Here we go. So I guess we should start at 3.1 lesson. And I was thinking on the way back here, walking back here, that one of the legitimate responses is, or two of them are, pause, meaning I got to think about that, and slow down. Just in general, forever till May. Because maybe I've said this. The good news, bad news is that this all makes a lot of sense to me, which means that I start to speed up. That good news is it's hard to stump me. Bad news is I start to speed up. So is there something on the lesson that I should go over in specific, or just even like all of example 1 or something?
Yeah. In example 1,
Also, I've been doing my teacher yelling, haven't I? Is this okay? Is this volume okay?
yeah, it's okay.
Right now, like this, if I pretend that I'm not yelling across a room?
Yeah.
Okay. I know. I spend days and weeks and months and years yelling across rooms, and I have trouble stopping. Go ahead.
Okay, so in example 1, in your video, you talked briefly about negative exponents.
Oh, negative exponents. So x to the minus 2 is 1 over x squared, for example.
Okay.
So if we have we were talking about K's and rate laws. So 0.30 molarity minus 1 seconds minus 1 is 0.30 per molarity seconds.
Okay.
Does that settle that bit, or is there something more?
No, that settles it. Thank you.
Okay. And then just to be extra, x to the minus 1/2 then would be 1 over x square root of x, huh? Does that work for you?
Yes, it does.
Oh, okay. Something else? Oh, I see here. We get to KP and then they do convert to KC. I swear those aren't in the real test anymore, but I'm going to say if I open one of those tests, here's the released international practice exam from 2016. And is it in the, here's all the K stuff. The conversion between KP and KC is not listed, therefore they can't ask it. So you know what? I may just go draw a box around this and do thonk. For next year. Or just eliminate, just, I don't know. Just say, right, yeah, find KP, but finding KC out of KP is not really on the table for them. Well, does that mean I should say backside or something? I don't know where we're going.
So during class, we were talking about number 3, but you got cut off because class ended. So
3 here?
Is that going to be on the test at all or no?
Oh, in the problems 3?
Yeah.
Oh, if the current version of the test, our test, has KP to KC or KC to KP, let's not have it. As a matter of fact, you know what I just did to this afternoon before this is I went back into the Word doc and changed this to KC KP equals 148 and took out this line. And I just made this given information so that this is the only part of the answer needed.
Oh, okay.
Because they can't ask this anymore, apparently. And I don't, well, maybe I'll leave it, I don't know. It becomes this whole philosophical thing, and I won't go on and on about it, but are you teaching a, quote, college type class, or are you trying to get kids to pass the test? And I have heard teachers argue both. The point is to learn a bunch of stuff. Okay, I got enough problems getting kids to pass the test. It's hard enough, in my view. Anyway, did you understand how this works, though?
Kind of.
Only kind of?
Yeah. I know where we get the 1.5 from. And I know you said that the answer was 148, but I was confused on exactly how we were supposed to get 148.
Oh, then when they did this calculation that we're not going to bother with, they got 148.
Oh, okay.
So if KP is 148, because KP equals all this, which equals this, put in the numbers, which equals 148. If KP equals 148, then you get this, products over reactants to the power of the number in front. So what we get then is square root of 148 times 1.5 equals PCL. Yeah. Pressure for the pressure for the Cl single, because we are calculating the partial pressure of the chlorine atoms, and we are kind of supposed to know that since these are Cl1s, they are single atoms, and since these are Cl2, they are bonded, and that makes that a molecule. So I don't know which one's the molecules. Well, the ones that have more than one atoms. If it has more than one atom bonded, it's a molecule. Not, these are just atoms?
Yes.
Okay. Is that big enough on the screen also?
Yeah, that's big enough on the screen.
Okay. Did that solve 3 or not?
Yes.
Somebody got another thing, I assume? I mean, there's a lot to this one, right? There's a lot. We could just keep going. But did somebody get to 4 or 5?
I think the farthest anyone got today was number 3.
Okay. Anything about 1 or 2?
No, those were just like, I don't want to say review, but those were like review questions, right?
Well, 1 I didn't actually bring up with y'all. Let's see. This, okay. In case this needs to be said, and I need to go back and see what we got here. We have a certain reaction, right? And K is products over reactants to the power of the number in front. Fine, right? I forget why it says half in my handwriting. I'm going to erase that. I'm sure I had a point. Did I make it in the? I think I was saying you could divide all this by 2. You could say 1 and 3 halves and 2 would be another legitimate way to say it. And you actually see that sometimes. But anyway, this would be the same ratio, right? If this was 1 and 3 halves and 2.
Yeah.
Okay.
Yes.
Okay.
Yes.
So here's what they did. Here's what I'm saying. How is what happened to here's exactly it. What happened to get this? You took this one and multiplied everything by half, right?
Yes.
So if you're going to change this up though, K mathematically changes. You know, that is a bit weird. This is more just an exercise. I can't think of any time when you would want to do this. It's just sort of a mathematical example. If you take a reaction and you multiply it by a half, what happens is, because they multiplied it by half, what happens is this K was true for this reaction. So the new K prime, will be to the power of the multiple you just used. How did we get from here to here? We multiplied by a half. So you can take the old K and use as a power the multiplier that you used to change this reaction into that one. So if we doubled it to get, here, let's do it this way. Look at it this way. Let's pretend we don't know A, right? This is K. If you double it, double the reaction coefficients, what do you get? You get the square of the K you were using before. And what's the square of square root? Regular version, huh? I have a feeling that didn't really land.
No, sorry. I was talking to someone. But yes, I understand what you're trying to say.
Annalee, repeat on that part?
No, I'm good.
Okay. Well, in that case, I will then say, so let's see here. Oh, then they run this one backward. So reverse this one and you get, reverse A and you get C. So then all the products become the reactants, all the reactants become the products. And so all the K calculations flip vertically. And if you take the new top divided by the old top, you get the inverse of the answers. You get 1 over whatever you got last time. Although maybe you already got that and I was kind of beating that down. I don't know. Anything else on 1?
They're writing EQ just to show that it's at equilibrium, right?
K is only true at equilibrium, but yeah. And also, it's assumed that you're going to be using concentration or molarity. Plus, they put the brackets. I'm saying, why put EQ? Yeah, because it's at equilibrium. I mean, they're not going to, I can't imagine that they're going to charge you on the test if your math, if you write this out, they say, first of all, write out the K expression, right? And you don't put EQ. That's not the point.
Oh, so it's just like an extra step they took, but it's not necessary?
K gets used so many different ways in this class. Honestly, I should count sometime. It might be 5. We already had 2. We had rate law K, and now we have equilibrium K. So yeah, it just means that at equilibrium K. But the point is the math, not the EQ part. Should we, I don't know, repeat something on the left side, or should we try the number 4, which I haven't seen in a while?
I'm going to say try number 4, because that one is very confusing.
All right. Well, we have a reaction, right? So remember that Q and K are based on molarity and not moles. So if you're going to put these moles into a 2-liter vessel, what you're going to have to do is find the molarity. It's moles per liter. So the molarity of the hydrogen gas is not 0.5. It's 0.5 divided by 2. Oh, right. Wow. I know this is going to sound stupid, but wow, this is the beginning of class. We haven't done an ice box yet. Whew. It has been a while since I introduced one of these. It's been about a year, of course. Oh my gosh, this is going to come up. and to the point where we go, and then you do an icebox, you figure out X, you put now that we've done that, then comes the new part kind of thing. A lot, like when I say find molarity, it's not supposed to stump anybody anymore, right? I hope. So what we're going to need to find Q is the molarities. Well, how do we know we're going to find Q? Well, let's keep on reading. So you have this many moles and this many moles and this many moles, and that's a 2-liter vessel. Okay. And it's allowed to reach equilibrium. Calculate the concentrations of all 3 substances at equilibrium. Okay. Here's the thing. They put these gases in, and then, and I almost can't say this strongly enough, and is allowed to then reach equilibrium. When they put these in, it's not at equilibrium, probably. I mean, they didn't say it was. It was allowed to then reach equilibrium. Are these the values that would mean that this system instantly is at equilibrium? I'll bet they're not. So at the beginning, our initial amount, right, was 0.25. 0.5 divided by 2 is 0.25. And these are all molarities. Oh, it even says molarity, right? People get sick of writing the M, so it's just kind of assumed unless you make a big point of it. And then 0.75 divided by 2 is 0.375. Yeah, this is getting into some real AP stuff here. Okay, here we go. So, is this at equilibrium? How should I know? Well, if you do the K or Q math, what do you get? We get products over reactants to the power of the number in front, but you have to use the molarities and not the moles. Let's take these and put them into the Q math. Let's find Q for just that moment when we put them in to the container. So this to the power of 2 over this to the power of 1 over and this to the power of 1, which is what they said here, right? What do you get? 2.25. Okay. Is it at equilibrium? I don't know. Well, did you get K? No, K is 0.02. We're going to have to start to convert these in our heads be able to convert them quickly. That's 0.02.
Could you repeat that? Sorry, my internet's cutting out.
Okay, which part? Like what? This part?
Yeah, the last sentence that you said.
Oh, I'm saying that it really helps to be able to say in your head, oh, that's 0.02. The decimal is 2 spots smaller, right? So 0.02?
Yes.
So when we did the Q math, did we get K? No, we got something over 100 times greater, huh?
Yeah, that's way bigger.
It's way bigger. 0.02 is not big, even if that doesn't look big. 0.02 is way smaller. So Q is much bigger than K, EQ, right? So is it at equilibrium? No, not by a lot, it's not. If it was at equilibrium, this math would have yielded that number, but it didn't. So first of all, is it at equilibrium? No. Okay, in that case, things will change. It was allowed to reach equilibrium. It will shift. It will start reacting until such a point when it does hit equilibrium. So which way is it going to shift, which we actually have to, I think, figure out first. So this is bigger than that. So at the current state, before we're going to hit pause on the time in the vessel and just pretend we're God and we can pause time, when the numbers were this much, you get way too much for K. All right. So which way will it go? Do you have too much numerator or not enough numerator for it to be K?
Would it be too much?
Yeah, this is too big, right? So I have
Yes.
too much numerator, too much top.
Too much top. We have to make it smaller.
Ah, very good. So this reaction though is going to shift until K is true. So is it going to get more products on the top or less products on the top?
Less products, so it would move to the left.
Exactly. So this number has got to go down. This number then will go up because when this reaction runs to the left, you destroy some of these and you make those. So this reaction will happen in one way or the other, one direction or the other, right? Excuse me. Yeah, one direction or the other, right? I'm just making sure that these are in the same direction. They didn't flip this one in here. Okay. It will happen either to the right or to the left until K is true. I have too much products because my number is too big. You are right. And this is going to go down. It's going to run to the left, and this number will go down, which means these numbers will go up from these points. This will reduce. These two will go up because as this is destroyed, it creates these. Does that work so far?
Yes.
Okay, so we said this one, now we've discovered, aha. And we could not know it without doing this. We have discovered that the reaction will run more left until it hits equilibrium. So if you want to write it the same direction here, that would be helpful. If you flip, well, I don't want it to go left. I want it to go right. And I'm smart enough that I will just turn this around. Okay, but then K has to be flipped. So make a choice. It doesn't super matter. But hi East, we're obviously on number 4. You kind of came in the middle. Can I spend, I'm going to try to, East, are you on not mic again? Are you on chat only? I'm going to pull up the chat. Yeah, okay. Well, East, here's some quick background, but it's going to have to be kind of quick. We had this many moles of this and some moles of that and some moles of that, as they say up here. But we're in a 2-liter vessel, so we divide everything by 2 because molarity is moles per liter. So this isn't 0.5, it's 0.25. Then we put all that into K math, but we use the numbers before it went to equilibrium, which means what you get for an answer isn't probably K, it's called Q. Q is just that right now, K, just right this millisecond. Did we get K? No, this is much bigger than that. So is it at equilibrium? No, if it was at equilibrium, we would have gotten this number. We got a number that's much bigger. So we have too much numerator, and the numerator is from the products. So we have too much products, and that was very quick, and I'm not sure how much that absorbed. It would be tough for me to absorb it that fast, but anyway, here's where we got to before for everybody else. So this is going to get destroyed, right? If we decided it's going to go left, because this number's got to go down, these numbers have got to go up. This is going to get destroyed, so it's going to have a subtraction out of this number, isn't it?
Yes.
And these have got to go up, right?
I might be jumping ahead, but are we getting the minus 2x because that is the number in front of HI?
Ding, 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 ding. Exactly the next thing I was going to say. And what's the ratio for every one of these that's created? The same amount is created, right? Because these are made one of these and one of those.
Yes.
And how much of this is destroyed? Twice as whatever you just said here, huh? You destroy 2 of these to make one of these and one of those?
Yep.
So if some amount is created, the same amount is created, and double that amount is destroyed. So when this all gets done, doing its reacting thing, and settles down to equilibrium, what you'll have is this plus whatever that amount is, this plus the same amount, whatever that is, and this minus double whatever that amount was, double whatever that amount was, but subtract it out. Take a moment, run that through your brain, because oh my gosh, is that going to come up? I would rather take 5 minutes getting this through everybody's head right now than have it fall apart later. Some weeks it seems like this is half the course, sort of. So let's get this working now. Does this box make sense to you? If not, ask why that, or what's that, or how did we, and I'll repeat it.
Okay, just to make sure.
Those dogs are amazing. What?
Okay, sorry. There's a dog barking.
Yes, I can tell.
So, no. Okay, so the initial is what we have at Q. Our change is what we need to add for it to get to equilibrium, and our equilibrium is what we get at equilibrium.
Yeah.
Obviously. Like that's our total.
Right. So at equilibrium, we will have created something, right? Some amount. Okay. For example, these are dumb numbers. I'm completely making them up. But if we know we're going to make 0.3 of this, then that's 0.3, and we'll get 0.55.
Yes.
Okay. And whatever you just made of this, you have to make of that, because when you destroy these, you get one of these and also one of those in exact equal amounts, right?
Yes.
So if somebody said, hey, by the way, I'm going to tell you, you're going to make 0.3 molarity of this. Okay, so 0.55. Well, then I can say, aha, so then you'll also make 0.3 of this one, huh? And so that would be plus 0.3 molarity, and then this would be added on to whatever this said. These don't have to match. They just do this time. Maybe they don't in future, okay? So just for a second, if this is 0.1, I can say, oh, we're going to make 0.3 of this, 0.55, which means I'll make 0.3 of this, which means 0.4 of this, huh? If it started at 0.1, pretend?
Yeah.
Okay. And I will destroy twice whatever we just discussed over here. So I'll be subtracting out 0.6 of this, which I just realized doesn't make any sense because you don't have enough to destroy that. But okay, stupid example. But if this was, 0.8, then we'd say destroy 0.6 and get 0.2.
Yes.
I do have the chat up, East, so chime in. At which point, we can say, oh, so these would be the amounts at equilibrium? And I know that if you do products over reactants to the power of the number in front, which means I have to square this one, right? Because there's the 2 in front here. Oh, he says, what's the X represent? X means as this shifts to the left, some amount of these will be created. How much? I don't know. Something. X. So here, if I tell you 0.1 of this is going to be made. Okay, so 0.1 will be made. I'll be adding 0.1, so this would be 0.35. Well, the same amount will be made because if you get one of these, you get one of those. So if you make 8 of these, you make 8 of those. If you make 90 kabillion of this, you make 90 kabillion of that. And if you made 0.1 of these, you made 0.1 of those. So 0.25, whatever this is, plus the same number we said 0.1, fine, plus 0.1 is 0.35. Just for fake dumb numbers. But we're going to destroy twice as much. So this would be minus 2 times whatever we just said. So this would be minus 2? Because we said 0.1, right? Twice 0.1 is 0.2. So we take this minus 0.2 and get, well, 1.7 or 0.175, right? He says, okay, all right. So I don't know what x is, right? But we know that if we do products over reactants, the power of the number in front, we at equilibrium, we will get this number. It is a fact of nature. So products over reactants, the power of the number in front will equal that. Yes, it will. It just will. And I notice on this one, we have a trick up our sleeves and we don't have to do the quadratic formula because look what we have. We have something squared over something squared, huh?
Yes.
So what we can do is square root all sides. You can't just square root the left side, but you can square root both sides. So what we can do is I'll square root the top, which is just cross out the 2, the squared exponent, right? I can square root the bottom, which is cross out one of these. And don't forget to square root the right side. And square root of 2 is 0.141. But it wasn't 2, it was 0.02, right? Well, you might remember if you're working on the number line between 0 and 1, when you square root a number, some number, instead of getting smaller, the number gets bigger in this zone. What's the square root of 1/16?
.25.
Oh, that sounds like someone used a calculator.
Yeah, I did.
Okay. Bad student. Bad. Squirt bottle. I'm kidding, sort of. Isn't that 1/4?
Yes.
So it moved toward 1, didn't it?
Yes, it moved towards 1.
So when I say square root of 0.02, it's actually going to get bigger. Anyway, plus this kind of problem, they wouldn't ban the calculator. You would get a calculator. But anyway, I keep trying to teach mental math skills. And also, it sounds like maybe no one made that point or people forgot. I don't know. Is this something that's come up in math class and been made real explicit? When you do square root in this zone, the answer gets bigger?
They may have said something about it in like freshman or middle school math, but I don't remember it.
Okay, well then I'm glad we hit it. So you have to take square root of this, which is that. So now I have this over this equals that. Here's what I did. See here. Did I mess this up? It's possible that I still have a mistake in here. This is that, and then point. I think I skipped ahead. Here, I want to do this for realsies. Okay, so this square rooted is this. This square rooted is cross one of these out. So we get 0.375 minus 2x over 0.25 plus x equals 0.141. Yeah, that seems right. Oh, that's what happened. Okay, right. When I take this and I multiply it up there, I get this. That's what happened. I just was running out of room. In case somebody wants to say, write all this out. So here's that after we square rooted. Then we multiply this over here, and we get this. Then push the x's to the same side. So I'd like a positive x, so I'm going to push this one over there, which gives me, I have to add it. That's a 2, because it's really light. So I add this to that, gives me this. I subtract this over, which gives me that. And then divide, gives me x. Which, you know, maybe isn't more complicated than they would ask. Well, actually, there are some, there's some actual solving problems eventually in some of these where I actually have to stare at the paper a little bit. So that is not out of the question there. Should I explain this part again for somebody?
Yes, can you explain it one more time?
Yeah. Okay, so here, I'm just going to start over here. There's a start. So are we good? Who was that? Was that Annalee said that? I'm not sure. I didn't look.
Yes, it was.
Okay. We get and you can say no. Are you good with this part that what I'm doing here? Do you know why this?
No.
No. Okay. We said K is products at equilibrium, right? Products over the reactants multiplied, all to the power of the number in front. So this is the numerator to the power of 2. This is in the denominator to the power of 1. This is in the denominator to the power of 1, which gives us this business here.
Mm-hmm.
And that's all equal to K. What's K? Well, they told us back here.
Mm-hmm.
Okay. However, I need to solve for x, and if you, this is going to give me x squared in here, isn't it? And x single. When you what do you? It's like anti-factoring. What do we call that when we combine these? Anyway, I am not math classy. Is this a binomial? I don't even remember anymore. No?
I think so, yeah.
Well, we're going to get, this is a quarter. A quarter of a quarter is an eighth, and then we're going to get x single, and then x squared. What you're going to get is some no x's, 1 x's, and x squareds. X to the first, x squared. You're going to get you're going to get the kind of equation that needs the quadratic formula, which is a huge pain in the neck. But this one has a loophole because it's essentially here. Sorry, how about this? What we've got essentially is that, don't we? This squared and then that is this squared, right, isn't it? So what I can do is I can square root everything, and then I won't get that whole business. This square rooted is, oops, of course, just that. This square rooted is just that. Square root of that turns out to be that. Does that work so far?
Yes, it does.
Okay, let's move this over. So 0.375 minus 2x equals this times that. And I'm going to cheat because I worked it out before, is, so this times that is 0.0353. Well, it's not going to be much. Yeah. And then we have to do this times x. Well, it's obviously just 0.141x. Let's shove the x's together. I want a positive x, so let's do that this way, and let's do that one that way. So on the right side, then we add 2x, so we've got 2.14, whoops, 41x, and then we subtract to the left, so we get this minus that.
Could you scoot the paper down, please?
Oh, geez, up. I find that students these days think the screen is going to go down. No, the paper is going to go up. Anyway, I add this over to get rid of it on the left side, so we get this. I subtract this over to the left side, and this minus that is that. And then divide, and cheating, the answer is 0.16.
How did you get 0.16? Because I did the same thing and I ended up getting like a crazy high number.
It can't be, look, it can't be high. Look, this is being divided by a number about what, 8 times itself? Okay, 6 or 7 times itself, right? It can't go up, it's got to go down. When you divide by a bigger number, you get a smaller answer.
Oh, okay. I see where I went wrong. I divided 2.141 by
children.
340.
Children.
Did it the wrong way.
Yeah, we've all done it backward before, huh? And what does your calculator actually read out, by the way, when you do that?
6.297.
6 point? What? Yeah, like 0.16? I don't really know. Well, if I use these rounded off numbers, Naomi, I don't see what you mean. I admit that these are, actually, these aren't rounded off. These are given in the, essentially given in the information. This is a slight round off because the square root of 2 is, well, square root of 2 is that, but it's not much of a round off because I've got 2 decimals in it. Or in fact, 0.1, no. Here, square root 0.02. There we go. And then this divided by that, this goes under, and we get 0.16.
Yes, I found out my mistake.
Okay.
I got it.
Well, here's the other thing though. We found x. X is the amount that gets added to this, isn't it? And subtracted from that?
Yes.
So go add them. So what will it be at equilibrium? 0.25 plus whatever x turned out to be. So go and add it. Oh, it's that. And these are the same number. So this equals that. They both equal this. And I gotta bail out of here right after this. I just realized with the time, and I'm supposed to be in North Victorville at 4. So we will take double whatever we just said for x and subtract it out of that. And that's how we arrive here.
Would we replace these numbers in the icebox, or would we write them separate?
They would say something. No, here, calculate the concentrations. We did. There they are. Calculate the concentrations at equilibrium. The icebox is a method to get kids to place the numbers in the right places so that they add and subtract the right things and so forth. It's just a method to set this up. And I know it might seem like that's not really possible, but in 3 months, you really might be saying, oh, sure, icebox, got it, right. Okay, and therefore this, and not even drawing that out.
Okay, I understand now.
It's just a method. If you can visualize your way to this, good for you, I mean, you can't just, on the real test, you can't just start writing, final answers. They want to see some workings out that you didn't just copy the last final number off somebody's paper. But you don't have to draw a box. It's not official. It's just been proven very effective at illustrating what's going on. Is there something else last moment?
I don't have any other questions at the moment.
Okay. Well, I think I got to go, guys. And I'll remind me to put this up if I forget later this evening. All right. Bye.
Bye.